So question 6 here, we've got it's titled Elements of Mechanics. So this question has a number of mechanical considerations. And first, in A, we have a light object with a small mass and a heavy object with a larger mass, and they have the same kinetic energy. Explain which of the two has the larger momentum. Okay, so a couple of important things. We're going to need the kinetic energy formula. EK equals half mv squared, so we've got mass and velocity, and for them to have the same kinetic energy, with one having a larger mass, the other one will clearly have to have a smaller velocity if it has a larger mass. The other formula, momentum, P is momentum equals mv, and we have to use these two equations in such a way as to find out which of the two has the larger momentum. Okay, so the EK is the same. Now, we can rewrite these things or use these equations in such a way. If we know the kinetic energy is the same, then half big mass, small velocity squared should equal half small mass, big velocity squared. Okay, that's a very useful way of noting, of using notation of the variables. Big M for the big mass and small v for the small velocity, small m for the small mass, big V for the big velocity. And straight away, just to make it easier, we can cancel out the halves because that's the same on both sides. And what we're looking for here is to find, I think, because we're trying to find out which has the larger momentum, so we're trying to find both momentums, let's see if I get this right, in terms of the same variables. And then you can see which one has a greater, if you like, proportion of those variables present. So there might be a constant which is larger in one of them, which will indicate we have a larger momentum, or there might be a square or a square root or something like that. So that's what we're aiming for. We're going to find out the momentum in terms of the same variables. So to do that, we need to know probably the velocity in terms of each and the mass in terms of each other. So if we can perhaps eliminate some of these variables so that we've got the same, we'll progress and we'll see what we end up with. Excuse me. So let's start with big V, because it's a little bit easier, and that's the process that the answers are going to use. So big V is going to equal big M divided by little m times v squared, and we will square root all of that. So we could rewrite that ever so slightly as the square root of big M over little m times by v. Okay, big M over little m square root times by v. Sometimes I put this little tag on the end of the square root just to remind myself when I'm writing that that's where the square root ends. Perhaps it might be better to put the v in front instead, but we'll move on from there. Okay, so let's see now if we've got it reduced down enough to be able to tell which one has the larger momentum. We'll do the momentum of the large mass. So I don't know if I can do this as a big P. Well, it doesn't really matter because it's capital M, capital V. So we'll do it that way. Big P, okay, is and I'll call it momentum of big mass with the spiky pointed big M. Even though it's a subscript, it'll appear small. The spiky top can tell you that it's the big M. So it's going to be big. What have we got? Big mass times small velocity. And for the momentum of the smaller mass, small p, small m, it's going to be small m times big velocity. Small m times big velocity is equal to this. So we're going to put that, because that's what that whole equation is showing us, so we're going to put that in there instead. We've got mv, m, small v, times the square root of big M over m. Excuse me. So we can see that in part of this we've got the two velocities that are the same, we've got small m and big M is the same, and we just need to compare the two in a wee bit more detail. So what have we got? If we're comparing the two, we've got both small velocities, so we can cancel those out. And so for the momentum of the large mass, it's capital M. And because it's not really an equation, it's easier to look at this as a ratio, because one's definitely going to be larger than the other. So that's M to, now when you, no, okay, I'll just put this in as is, M to M over square root of big M over little m. Okay, so let's see what's the next step. It might be useful to write, just to make it a little bit plainer, these in terms, that's m to the power of 1. This is m, if we take the 1 over square root of m, that's m to the power of negative 1/2. Square root is to the power of a half. This is 1 over square root, so it's to the negative of a half. So we might be able to do a little bit of cancelling there. Let's just rewrite this in a slightly more user-friendly way for that purpose. M to the 1 times by m to the negative a half times by square root of m. So we're mixing our notation, but this is going to help us cancel out some things. So with this m to the 1 and m to the minus half, when you're multiplying same things, same variable with different powers, you add them. So that's going to be 1 minus a half gives to the power of a half. So that's going to be equivalent to just a square root of m. And that means we've got our final, well, a step anyway, m is square root m over m times m. These are both square rooted, because remember, you bring this square root down here. It's square root of small m, square root of big M. So we are right there. And how, excuse my ums, I've just become aware that I'm saying a lot. We can see hopefully straight away that this is going to be larger, and we can perhaps work out a factor by which we would have to multiply the right hand side, that's on the right, to reach the same value as the left hand side. So if it was just square root of m by itself, we would have to multiply by square root of m to get m. So we've got to multiply by square root of m, and we also want to get rid of this other square root of small m. Forgive me please for forgetting to say whether I'm talking about a small m or a large m, but hopefully the notation's clear. So we want to get rid of the square root of small m up the top, so we have to divide by the square root of small m. So this factor here that we have to multiply by to bring the right hand side, or the momentum of the small mass, up to the momentum of the large mass, means that the momentum of the small mass is the one that is smaller. Whew, that was a lot of fun.